But the midnight sleep so that aspect. Spring 60% close. Just like that's the best part. Experiencing some also today's amazing. We're just like okay, it was like I'm going back to the gray skies. Yeah, I think it's good. I'm 11 to 9. I think that's all you mentioned. Is it real, right? It was not. It's just I was following you on social what else I don't know if I can. Because no. I met up with you. Here we go. The hours of it's like holy shit, it's monopoly.
I've pressed it several times. Should just
Can you turn it off again? Yeah. Done. Yeah, it will take a moment. Yeah. Or just go ahead with one screen.
That's lovely. Actually, when I came but then
Right. Hi, everyone. This is really annoying, but I can't get this projector to write ideas. And please step forward now and let me know how you do. But I've tried everything. I don't know what to do. It just won't show. Is this a normal thing? Does this happen every week, or is it?
No.
So it's just me then. All right. Any bright ideas, anyone? How we go about this? So you're going to be able to handle it on the one screen? Otherwise we're here for like 10 minutes trying to sort this out. That's the problem. Shall I just carry on? Are you all right? Yeah. That's good of you. All right. Fantastic. Right. Welcome. Where are we at? Right, so my name's Ben. And about 6 years ago, I used to be the director of this master's program. Those were the days. And every now and then they asked me to come back and give a lecture, so here I am. And this is the first of 2 lectures on biodiversity. We're going to start with some talk about how we measure biodiversity, sort of general overview, how we measure, like, there's a lot we could do I know it seems like a very niche field in economics, right? But there's actually quite a lot we could do. I also want you to know that there's a lot that can be done in biodiversity, so you're going to see a lot of different things going on in this lecture about biodiversity. Broadly speaking, the first lecture is going to be about sort of some theoretical ideas around biodiversity, particularly in terms of measurement, but also in terms of valuation, right? Next week, the lecture is going to be more about some of the absolutely amazing empirical work that's been going on in economics, in the economics of biodiversity, which also will be mind-blowing. So yeah, that's the basic idea. So yeah, that's me. I'm the Dragon Capital Chair of Biodiversity Economics. Can you imagine? So I'm funded by, and this is a measure of, in a sense, of how important biodiversity has become as a topic more generally. I'm funded by a Vietnamese asset management company whose chairman is an English guy who went to Exeter University, with big philanthropic ideas. is just pays for a chair in biodiversity economics at Exeter, right? And he does that because he's interested in managing his fund in a way which is a bit more kind of organised and switched on to nature and nature-based risks as well as impacts, right? So it comes from there, the chair and everything like that. But obviously I've been interested in biodiversity, the economics of biodiversity for many years. Okay, so this is the structure, measurement and metrics today. Measurement and theory. We're going to look at some metrics. We're going to look at theory of risk and insurance, the idea that diversity can be an insurance mechanism, and some innovation values as well. Next week, empirical, causal inference, that sort of thing. And some kind of impact evaluation stuff, typical program evaluation, causal inference. What works is the basic question in terms of biodiversity conservation. So, a good place to start is with the Dasgupta review. So I imagine you've all heard, as you transited through this course on climate change, environmental economics and climate change, you'll have heard of the Stern review at some point, yeah? Right, that was Nick Stern and Tony Blair and Gordon Brown, those people you probably never even heard of, but they were important at the time. They funded that. Now, recently in 2021, the Treasury also funded a review on biodiversity, and that was done by Partha Dasgupta. Has anyone heard of the Dasgupta review in this room? Hands up. Okay, that's more than last year. That's kind of interesting. That's good. So, and the kind of basic idea, so this is really stepping back overview, the basic idea is that contrary to kind of the sort of mainstream of macroeconomics, there are some sort of limits to growth. And some of those limits come through the fact that, as he describes it, the economy is embedded in the biosphere, which means that you can't model these things really separately from one another, which would be typical in sort of growth economics in general. These have two-way interactions with one another. And sort of his point about all of this was that actually, so this is just really high levels sort of messaging here, but this GS here is this natural resource modeling, like a fisheries model type idea, like the kind of biomass that you get from S, this biodiversity, is what you get back from biodiversity, and actually to sort of saying that the kind of impact that the economy is causing upon biodiversity is greater than that renewable output, right, from biodiversity. So we're doing too much, and we're heading towards some limits, and growth is going to go down. There's a more formal model in the review, chapter 4. Right? So this comes along with the kind of general ideas that you've heard about, that GDP ignores the impact on natural capital and wealth and so on, and so the signals that we're getting in terms of economic policy are all kind of wrong, and then typically biodiversity is not priced in there. So 6 trillion at least of subsidies towards biodiversity harmful things like pesticides, fertilizer, to some extent fossil fuels that cause climate change, which change ecosystem services and things like that. So some transformational changes require a non-zero price for biodiversity and decision making, and we need measurement, we need causal insights on what works to kind of conserve biodiversity and also feed through to funding conservation. Okay, that's the kind of big picture story that the Dasgupta review gave us about biodiversity. It's all going wrong, and you know all of those things. That's a story that you're very familiar with, I think, right? Thinking about natural capital and shadow pricing, natural wealth, and so on. So that's the backdrop, right? So what we need to do here is think about what exactly biodiversity is, right? And how we measure this. Then think about how valuable this is to society in some way, right? And those are kind of interesting steps. And then we need to know, okay, how are we going to change policy in order to ameliorate some of the damaging effects of climate change, or even improve the regrowth of biodiversity and all of the ecosystem services that underpin it. Okay, right. So the first step here is, how do we measure it? Right? What is biodiversity? How do we measure it? As economists, we like to kind of maximize stuff, and so we need some kind of metric here that we're going to be organising around, and yeah, that's what we're going to talk about now. All right, so what is biodiversity? So here's, this is one of the readings, Baumgartner 2006. It's a wonderful paper, it's never published anywhere. I'm trying to get him to write something with me on this, to get this sort of stuff out there. But it's probably his most cited paper, even though it's just a working paper. So it asks the question about how do we measure biodiversity. So what do you think about all of this? So here's two samples. You can imagine that you're interested in measuring biodiversity, you're walking through the rainforest somewhere or whatever it is, and two different places. You want to know which is the most biodiverse because actually you've got a limited budget and you want to basically organize your resources around saving as much biodiversity as possible. Okay, so our metric is super important. Okay, so we've got sample A, sample B here, right? So sample A, what do we have? We have some butterflies, we have a ladybird, we have a dragonfly. Okay. And sample B, we have ants and some other type of butterfly. So, hands up, who thinks sample B is the most diverse here? Okay, you think, okay, that's good. There are no wrong answers here, so that's fine. So, presumably, the rest of you think that sample A is the most diverse here. Would I be right about that? Yeah, why is that then? Why do you think that? Well, actually, no, let's start with you. What's your story?
I was thinking, clearly the A has dominated by butterflies, right? And that's not a sustainable ecosystem, so the other two animals will probably die soon. Anyway, so I would put my resources in the ecosystem that still has a chance to stay sustainable, to stay biodiverse. Sorry.
All right, so there's a lot going on there, but I think we'll see if anyone changes their mind and fits in with your definitions here, right? Okay. All right, so mainly A, and your name is?
Mario.
Mario. You're B. Okay, brilliant. Okay, now I'm gonna think about this. Okay, what about this sample now? Imagine that we got this sample from place A and then the same sample from place B. Now which is the most diverse here? Is it A, like all of you thought before, or is it B? Hands up who's changed their mind. Okay, a couple of people changed their mind, some oscillating. All right, let me help you out here a bit. What about now? Is this sample more diverse than this one? Okay, so those of you who were thinking A here, what was your rationale? Tell me. Yeah, you.
I was thinking, obviously, more species, so in a species sense, technically more.
Yeah, species, right? 3 there, 2 there. Okay, good. But then some of you changed your mind here, maybe. Hands up who changed their mind at this point. Again, yeah, so few people, okay. What about now? What do you think now? Right, we've still got our ladybird and our dragonfly up here, yeah. But like, which is the most diverse sample in this case now? Is anyone else? Who has changed their mind from the very first question now? Yeah. Who has steadfastly stuck with sample A here? Yeah. Okay. Interesting. So you can see that even with the simplest kind of sampling procedure, we are all disagreeing in the room about what we think is the best measure of biodiversity, and we have different stories going on in the back of our heads here. So the first one, Mario here, was basically really focusing in on the fact that there's an even distribution in terms of population of the species that were there, right? And to begin with, the A crowd, let's call them that, just focusing on a number of species, yeah? And then later on, when things get a bit uneven, you're thinking, actually, this does not look very diverse any longer. So you're switching back for some reason. So somehow your number of species become less important over time, right? All right, so the point is, it's just a bit tricky to come up with a metric for biodiversity. We're gonna go through a bunch of different ones now. And this is just, all we've looked at the moment are, like, there's a multitude. We've looked at species richness here, number of species. We've looked at sort of evenness and relative abundance, basically, as being a factor that we might think is important for whatever reason. And your reason was like ecosystem services as a functional reason for having even distributions which aren't dominated in some way, right? And like in reality, that would really depend on the ecosystem you're talking about, because some of them probably, in fact, really like to have uneven distributions, but you know, there are some boundaries to that. We're going to look at some others. So species richness, evenness. What is this missing already? We're not, you know, the species there were sort of somewhat distinct, but they were insects, right? I mean, that's just a bunch of different insects. And, you know, we could have had two species, one which was a plant, one which was an insect, compared to 3 insects. You might then think, well, actually, that sounds a bit more diverse with a plant and an insect. Maybe there's a mammal in there as well. You start thinking about differences between animals and genetic distinctiveness. So we're going to look at some of those measures too. This comes from, you've heard of Marty Weitzman, I guess. Has he come up? Probably prices versus quantities and dismal theorem and stuff. Yeah, same Weitzman did some really good stuff on biodiversity. Sorry, I've screwed up these things a bit. Yeah, so genetic distinctiveness will be looking at kind of taxonomic trees and how relatedness between different species and so on. And then, oh dear, this is not going well, is it? And then there's some other things called intactness, right? So you might measure how diverse a place is based on some reference point that you have about how intact it is, right? So sort of depleted places with fewer species than should be there are less diverse than ones which are more pristine. And the reason I mention these ones, well, we'll come back to them later. No, this is really not going very well, is it? Now we've got extinction risk, right? One of the chief reasons why we care about biodiversity in general, I would have thought, is that we're worried about stuff going extinct. So we can think about extinction risk as well, and that's what we're going to do. There'll be mixtures of these measures as well. All right, let's think about something. Right, it's going to be some maths now, so you need to like just deep breath required, and we're going to talk about things a bit more formally. So we can think about diversity as a function of different features that we've been talking about, right? So that's what the omega thing is. This is the notation from the Baumgartner paper. So that the omega could be thinking about sort of number of species, even relative abundance. It could be thinking about ecosystem functionality. It could be thinking about distinctiveness, number of ears, legs, you know, phylogenetic stuff, whatever. But in this case, let's think about this family of measures called the Hill measure, which is basically all about relative abundance, right? So you've got your sample of species, like we had in those samples there, and they appear in different populations, and they have different relative populations compared to the community population. Right? And the Hill measures basically take this relative abundance measure, PI. So PI is population of PI divided by total population in your sample, right? So it's like a proportion of the population that each species has, yeah? And it takes that measure, raises it to a power alpha, and raises sums over all of the different species and raises that to a power 1 over alpha minus 1, right? Okay, so this is like a constant elasticity of substitution wrapper for our relative abundance metric, right? Summing over I through to n, which is the number of species. Okay, so this is a family of metrics for biodiversity, which are trying, they're a bit like variance type measures, right? Do you think about that sort of, they're often known as pure diversity measures. So they're trying to get a sense of the spread within the sample, weighted by the populations in that. Okay. So we can take different values of alpha, and then that's why it's a family of different metrics. So if alpha is equal to 0, this just collapses to species richness, okay? Which was the A crowd. That was your metric. You loved that, right? Then you can think about these are kind of metrics you find in the discipline, like Shannon Weiner index. Alpha equals 1. Okay. This collapses to, there it is, it collapses to a sum of PI times the log of PI. This is like an entropy type measure. It's sort of used in information economics. It's telling you something about the information that's in this set of species that you've drawn. And then you've got alpha equals 2, alpha goes to infinity, alpha equals 2 is called the Simpson index, right? And the kind of intuition there in the end, that's it's 1 over the sum of squared proportions, right? So the idea behind this, so you don't have to get your head around this right now. I'm just sort of walking you through. But the intuition behind this particular metric is the idea that what is the probability if I draw out 2 of the species from my sample that they're the same species? Right? Yeah. So it's just a purely sort of probabilistic type measure of, you know, so the less diverse the system, the more likely it is you're going to pick the same species twice out of this system, right? Okay. And then you've got, if you go to alpha goes to infinity, you get what's called the Berger-Parker index, which is really all just determined by P1, which is the most abundant species in the sample, right? And how you can interpret alpha moving from 0 to infinity is like having more and more aversion to unevenness in the relative populations, right? So Maya, you had a fairly sort of, to begin with, fairly strong alpha, I would say, saying, you know, that, and I can tell you more or less what value you had in your head there in a minute, but like you had this aversion to unevenness, right, which nobody else did at that point, yeah, and that gets higher and higher and higher. So with the Hill measures here, you know, they have various qualities that we can think about. It's quite helpful measures that you see a lot in empirical work in economics. Do you know Charlie Palmer? Have you been taught by him yet? Anyway, he's our leader of the environment cluster. Yeah, so we have a paper together where we use these metrics to understand how effective agricultural policy was in the UK. I'll tell you about that some other time. But the thing is, we need to be thinking about the properties of these metrics before we decide whether we like them or not. And like some of them are here, you know, so they're increasing in the number of species, but sometimes not in AI. I'll come back to these later on. But like, bear in mind that you're going to see a lot of metrics for biodiversity coming up in the next half an hour. And we do need some way of thinking about which ones we prefer. Okay, so one way we can just kind of delve into that is just think about, you know, these different properties. Are they increasing in the stuff that we like, the number of species? Are they increasing in abundance, which is something else we might like? You know, sort of biomass, we kind of do like that for various reasons, right? Is it increasing in that? And sometimes it's not. And sometimes they have just no intuition whatsoever. So for instance, you might be asking yourself, like, why is it that we've gone from 0 to 1? Why aren't we using anything between 0 and 1 here? Well, it turns out that ends up giving you sort of really weird properties, actually, for your metric. You have sort of put a lot more weight on, well, actually, it's not really weird properties, but you put a lot more weight on really rare stuff. Actually, you might like that. It's true. Yeah. But they don't tend to do that. They tend to think about evenness in this context. Okay. So just to give you a numerical example, it's coming straight from Baumgartner. You know, you've got these are two sample systems, A and system B, that we were looking at before, you know, half-half versus different proportions here. And with A equals alpha equals 0, it's species richness. Of course, we prefer the first sample. And then as we go towards the Shannon Weiner index, where we still find the first one more diverse. So Mario basically had an alpha greater than 1.1, something like that, yeah? Because as you get more and more averse to this unevenness, then you switch over and you think, oh, actually, you know what? Now I prefer system B as my most preferable, most diverse system, okay? And that's just because you've got this aversion to unevenness for whatever reason. And you can think about it in terms of these probabilistic measures. What's the probability of me drawing same species? Or you could think about it if you want, and often this happens in terms of ecological function as well, right? So we actually prefer, we revert to unevenness because as it gets very uneven, you know, for instance, perhaps, you know, like with all those butterflies, that's a system that's not going to work very well. Yeah. Okay, so that's how Baumgartner introduces us to this measure, Hill measure, like family of measures for biodiversity. Okay. Okay. here's another aspect of biodiversity as well. So like this is, by the way, there's some R code that comes along with this lecture, which you can use to kind of do all these calculations if you want. I don't know if you're inclined to do that, but anyway, you can go and knock yourself out if you like at some point. But then another concept of biodiversity, of diversity at least, is alpha, beta, and gamma diversity. So this is Scotland here. We have a little square here. These are kind of 10 by 10 kilometer grids in the UK. We have data on bird diversity for the UK. We have a lot of bird watchers in the UK. I don't have. Is any bird watchers in the room? No. All right. But we do have a lot of them, and they go out every year. It's quite organised. They go to exactly the same squares, kilometre squares, and they walk through on exactly the same day every year. And they count up the number of species and the sort of the abundance of these birds every year, right? So you've got this data that goes back to 1992, I think. So you've got this really nice record of bird diversity, and this little square here is one of those records, right? And it's telling you something about the birds that are there. There's quite a lot of them, basically. It's about the abundance there. All right. If we look at that, square, and we did one of our, let's say, our hill measure type metrics of biodiversity, at that square, that would be alpha diversity. You're looking at like just this little bit. In the broader landscape, you're just looking at like a field or a square or whatever it is. It's just there. And then you could have another one here. There's another square down here, which has a different kind of level of diversity. You could have alpha measures for both of these, taken individually and so on. But then spatially, you'd think about, well, there are other measures as well. We could have, if we just summed these together and did the diversity measure over them, that would be gamma diversity. It's the kind of landscape level diversity. And then the beta diversity is the kind of difference between the two. It's like the between diversity. So yeah, think about your fixed effects estimators. Like you've got the within and the between variation. It's like a combination of those. So alpha, beta, gamma diversity is super important as well. Shannon index, alpha equals 1, quite handy because actually these concepts are kind of additively separable in this context. So it's just a kind of interesting, useful feature. Okay, so here are the outcomes here for these particular bird data. Okay. All right. So yeah, here's the code. You can go and have it. You can go and check that out. There's a Dropbox which you can all access at some point. Okay. I want to move on now. Here we go. All right. Okay, so those are kind of relative abundance type measures, and as we saw, they're kind of helpful for thinking through pure diversity subsets. What about dissimilarity, distinctiveness, genetic differences, and so on? Let's think about those now. All right, so Weitzman's done a bunch of stuff on this. It focuses on genetic distances between species, right? So you think about laying out their DNA. You can think about this on a table and then matching them up and seeing how similar they are. You can either count up the sort of letters and see how common they are between the two different species, and then that's your distance measure. Or remarkably, I found out today as I was reading, because I was thinking to myself, yeah, I love this paper I'm going to show you later on. I was thinking, okay, so how do they measure genetic distances? How did they used to do this back in the 90s? Because it's a paper from the 90s. And it turns out what they do is they get these strands of DNA and then they heat them up. And then they fall apart at this point. You can tell this is not my field, right? This is I'm just kind of layperson's explanation was given to me, and I'm giving it to you. The DNA falls apart, right? And then they hybridize the two species that you're interested in. They connect them up together, and then they heat them up again. And the temperature difference between the first stage and second stage is your measure of genetic difference. Because it takes a certain amount of energy. The more connected they are, the more energy it takes to split apart the DNA. Right? Isn't that mad? So if they're very unrelated, you only need a moderate increase in temperature. If they're really, really strongly related, it's about 1 degree per 1% of similarity. Yeah.
I was thinking for like.
No questions on this, please. I have no idea what the answer is.
Not in the method, but like
Right.
looking at the differences in the letter of the DNA, would I not see more the health of an individual species in a region as opposed to the health of diversity of the whole region?
Well, look, we're just talking about the, like, outside of species. You can think about them in the lab, basically. How connected and similar are they, right? This has got nothing to do with in situ, unless I've misunderstood the question.
Just think how like comparing the DNA difference between like a butterfly and a horse and a chimpanzee, like that. What information does that give?
Yeah, sure. It's a good point. So the context, that's good. Okay, so your question is about context. Yeah, so the context in which we would sort of think about these genetic differences as being kind of important for a policy perspective might well be, I mean, there are different contexts, but like think about crop genetic diversity, right? You might be thinking about how diverse is your wheat. You're thinking about different breeds of wheat and how diverse they are, and you might find that's important for functional reasons as well, so resilience and so forth. So there's that. It could be other breeds of like cattle. You see this done in cattle breeds, right? And so they're quite closely related, and you're just looking at their sort of heritage in that sense. With the birds, I mean, we use the genetic measure in the birds paper as well. And there, that's a tree example there, which we'll come on to in a minute, is another sort of context. So you can use these measures in that spatial context as well. But remember, it's sort of birds, right? So
this is for within a species. The diversity.
I mean, it doesn't have to be. It doesn't have to be. But I'm just saying that the context in which those metrics have typically been used, because we don't find it useful to compare horses with bacteria, for instance, is in where things are quite similar already, and you're thinking about that genetic grouping. Yeah. So yeah. Good. So this is what Weitzman thought about. So Weitzman basically has 3 papers. One called On Diversity. There's about 800 equations in that. I don't recommend you read it unless you're properly invested in this. The one I do recommend you reading is the 1998 paper, which is called the Noah's Ark problem. We'll come to that in a second. But it's anyway, this is the basis of the 1992 paper. Basically, he builds up a measure of diversity, W for Weitzman here, of a set of species S. And basically, it's to do with distances. Like, what in this set? What is the maximal set of distances that we have between the species in a particular set? And he builds it up by starting, like, the diversity of a particular set S is equal to the diversity of the subset Q, right, plus the distance between Si, an excluded species, and the species set Q. Okay, where this distance here, this distance measure here is the minimum value. So you're finding the closest relative for your species that you're about to add in to the species grouping that you have already. Okay, the closest relative, and that is the contribution to diversity that this species gives you. And then with some other conditions, you find the maximum of that process in this recursive process. You start with 0 species, you add them in sequentially, but at each point you're maximizing the minimum distance measure as you add it in. Okay. So that's kind of how he thinks about it. This is like a dynamic program, really. Yeah, which you've done a lot of, it turns out. So you can think about it with these guys here, the primates here. It's a brilliant paper by Calon Darnoldi et al. From 1998. So they give you the numbers and everything like that. I don't know what these are, where these numbers come from, but they're not temperatures. I can tell you that. This is more to do with like branch length of the taxonomic tree, which could also be like distance to last in years to the last common ancestor. That's another kind of way of thinking about genetic differences. So these are the distances that you can use to build this measure up. And again, we could go into great detail about this, but so here you've got the gibbon here and the gorilla orangutan, two types of gibbon, right? You've got the distances of the gorilla and the orangutan are somewhat closely related. The two gibbons here, they're the closest related pair, right? They're pretty related. 126 is the lowest number in this grid here. So when you're building up this measure of biodiversity from the Weitzman perspective, you're obviously going to be taking out the two. That's the minimum distance between an excluded species and the remaining set. Okay, so that's you'd be thinking about this distance here between the two gibbons, right? But then you've got a question about which one you exclude. Do you exclude the HYS or HYL from your metric? And this is where the maximization comes in. You have to choose the metric, which is the grouping here, which maximizes this distance measure. Basically maximizes whatever sum of these distances that you add up as you go through. Okay. So it depends then on whether this grouping is more diverse than this grouping, and anyhow, you can't tell this from here, but I've got an R markdown thing that you can go through. It solves this out for you. It turns out it's this one, right? Because it has the measure 889, which is the sum of this number here and the 532, right? So you exclude the HYS, and then once you've got the diversity of this grouping here, you just add in the 126, and the overall estimate is 1015. Okay, so it's a metric based on maximizing according to genetic distances. Okay, absolutely nothing to do with whether we like these species or not. Yeah, so this is a nice sort of example because we all, basically, I think, unless we're completely mad, we love these animals here. But it's got nothing to do with that. It's really to do with just, you don't even see a picture of them. You look at the genetic distances and you think, right, this is our metric of diversity here. We want as much genetic diversity as we can get. Okay? All right. So from that, you can draw like a taxonomic phylogenetic tree, which shows that effectively an interpretation of this is that the diversity measure is the length of these arms. So you've got the 532 is the difference between HYL and the gorilla there. The 357 is the distance between the orangutan and the gorilla, and then the 126 is the difference between these two. And this is the arrangement that you get from this maximization. So this is like a phylogenetic tree that comes from this metric. Yeah.
So does this metric also account for the interaction effects between these species? Because if you're far away from each other, then there's a likely chance that you might be opponents of some sort, or actually, have a higher probability of collapsing that ecosystem.
So this is a good question. I mean, what is the context in which we're going to use this? I mean, I've just told you that we don't even care. Like, you can imagine someone calculating this without even seeing what it is that they're looking at. They've just got numbers there, and they're just calculating, okay, that is more diverse than that. There's no functionality context particularly. It's really just taking the pure view that we are interested in genetic diversity per se, for whatever reason. And I'll come back to this in the next slide, okay? So, unless there's any more questions on that particular issue, yeah.
Maybe this concept would not really deal well with convergent evolution, right?
I don't know. Let's have a look. Explain.
So
Let's
if
explain
two
for everyone.
species are quite different, and so their last common ancestor is quite far
way back, yeah.
but they developed convergently to some similar trait to adapt, then they would be quite similar, even though if their last ancestor is way back.
Yes, that's a good point, actually. Yeah, so that is true. Yeah. So that depends on how you're measuring the distance. So if it is about last common ancestor, it misses that thing that you're talking about, which is actually kind of the actual genetic differences between them. So yeah, that's a really good point about what we're measuring in these trees here. Yeah.
Oh, I just wanted to respond to that a little bit. Generally, with convergent evolution, they've gotten to the same place in completely different ways for the most part, and so they wouldn't be like genetically very similar.
Yeah, that's true. No, that's a good point. Yeah. So So those two things, yeah, I don't know what a good example of that is actually. Do you know a good example
Yeah,
of
like
that?
if you think about like bats and birds, like that's a
Bats
and birds, like
Right.
that's a common example of like they both developed wings, but like completely different genetic ways of doing that.
Okay. Quite different, yeah. Bats and birds, pretty different, yeah. Okay. Good point. Let's not go down this rabbit hole too long, but I appreciate this kind of input because this is a blind spot for me. I'm not conversant in biology particularly at all, so what you hear is just kind of layperson stuff. Right, then we might think about uncertainty here and extinction risk. And so in the Noah's Ark paper, what Weitzman imagines is, and he really focuses in on his distance metric, right? So he's taken the paper from before and he thinks this is the most important thing. But now he's thinking about making decisions about species which are going to go extinct. So there's like a real policy context now. And he imagines Noah, right, stood in front of the Ark, making a decision about which species he's going to let in and which are going to be cast aside, right? And the only rationale that Noah has in his paper is to maximize his genetic distinctiveness, okay? Beautiful paper, quite heroically written, Cavalier style, really nice. But basically the idea is that you now attach probabilities of survival to all of your different species and you weight the distances by these probabilities of survival. And if you recognize this sort of formula, this is like the probability of survival, non-survival of each species in this set Q, basically, okay? What's the assumption behind this set of, like, this joint probability story that we've got here for each?
Independence?
Yeah, completely independent, right? So that's, you've got to be warned about. This we're going to look at in a second. This is going to be the example that we look at. Okay, it's just another tree here. But like he describes the species as being like books, and the genetic code being like libraries, and the species are like the genetic content of each species is like a library, right? So they have some shared books in them, J, and then they have their own specific ones here, right? And the question is like, how do we conserve the most diversity given that this is the way the genetic distances are set up? All right, so expected distinctiveness, we now have probabilities. Now, so that's expected diversity. Expected distinctiveness is like a marginal concept. It's the derivative of this expected diversity with respect to a probability. So you've got a policy lever here, you're changing the probability of survival, and you want to know how much you're going to affect this diversity measure, right? And so this comes out here, it's basically the same kind of concept, except now you've just got the distance here. For species I, you've got this distance between the species and the nearest relative in the remaining set. Okay, so it's the same kind of idea, it's just probabilistic and everything is weighted by probabilities of survival. Okay, so in the kind of two species case here, all of that before just goes down to here. Yes, with probability P1, P2, both libraries survive, so you get M1 plus M2 minus J. Right, so that M1 is like the sum of this, M1 is this sum here, M2 is that sum, and then you minus J because you've got, it's a shared diversity. With probability P1 and 1 minus P2, only library 1 survives, and only library 2 survives, and neither survive. Okay, so you've got your metric of overall diversity ends up just being P1, M1, P2, M2, minus P2, P1, J, the shared books in the library. Okay? Then the marginal concept here becomes the derivative of that with respect to P, that's your measure DI of distinctiveness, which you're interested in at the margin. And this is the thing that Noah is going to get really concerned about. Like, what is this species bringing to the ark here in terms of diversity? Yeah? So once you do that in this context, you end up with the library 1 having measure of diversity equal to M1 minus P2J, and then library 2 is M2 minus P1 J, right? So you end up with a situation in which it's possible that if the diversity is quite similar, I mean the kind of distance of these genetic arms is very similar between these two, then you're going to prefer library 1. Oh yeah, and the probability of survival is higher for sort of species 1 than species 2. You're going to prefer library 1. Okay? That is, you do not focus in on the species which is highly likely to go extinct. Right? You want to nail down, you want to nail down the books in the library, not just the one for the specific to the library, but also the ones that they share. Yeah. And so this is seen as it's a bit of a topsy-turvy way of thinking about biodiversity conservation, where we generally think about focusing in on reducing extinction risk. Okay. Okay. Oh yeah, and then in the paper he comes up with a rule for NOAA to use to rank the different species. And yes, it's dependent on the distinctiveness measure. It's dependent on this cost effectiveness thing, how much can we change the probability of survival and how much does it cost? And then it has this bit in here, which you can tell one of the referees of that article told him to put in there, right? But it describes it as, this is utility, right? So at the moment, this is completely divorced of any value that we might want to put on a species. The fact that we like it, it's cuddly, it lives here or there, it provides us with food, whatever. We don't care up until this point. But one of the referees clearly said, you might want to think about the fact that people value different species. So he put this in. And he says, this is just to account for the fact that we might prefer elephants to mosquitoes, basically. All right, but that's the point. He's trying to get away from that kind of willingness to pay for biodiversity kind of argument that was prevalent at the time and still quite prevalent. All right, and you can estimate this. It seems really complicated, but there's data out there you can use. There's data and there's code out there that you can use to estimate these diversity metrics for the UK. So we basically, these are two spots again. We've got all of these data. We can estimate the genetic tree for this group here. You've got ducks, you've got crows, you've got troglodytes. Troglodytes is the smallest bird indigenous to the UK. It's called a wren, and so on. And then the other is different, and then you can build up these measures. In fact, the one that we use is basically measuring the branch length, so it's a bit more like distance to common ancestor. Yeah. Okay. So you can play around with that if you like. Any questions about that? Yeah, tell me.
Why?
Why? Can we narrow it down a bit, please?
I don't know, I was like, curious, like, increasing biodiversity at this like mathematical feels like you're not actually achieving like saving the environment, the natural environment. Because like every time I was constantly in my head thinking that like, if you want to improve biodiversity in Greenland, you wouldn't save polar bears, you would introduce penguins, because that's a whole totally different thing. So I don't like.
Yeah, but I didn't say that probability was being changed, did I? In the context of Noah's Ark, it's you're not going to drown, you're going into the Ark. In the context of polar bears, it's we're going to introduce penguins, and we're going to spend our money on that. So the point is just really about like how we're going to. We have targets for biodiversity. How are we going to do this cost effectively? And what's the target really about? We want to do genetic distinctiveness, or do we want to count up species, or what is it? Yeah.
I get the idea that we need to simplify things, but like there I'm struggling a little bit with. We don't at all think about, okay, how many other species might like depend on this species, and like this, it's such a complex ecosystem, and like it can collapse.
Yeah,
right?
yeah, good. That's really true. Yeah, I mean, so there are extensions to all of these papers, which are from the 90s, which build in correlations between species. So this dependency as well, if you wanted it, you could do it. These days in particular, you don't get nice analytical results like these, but you can do this numerically, right? No problem. Yeah, you have to know these correlations pretty well. So there's no problem with that particularly, right? But I think the question is like, what is it about biodiversity that we're really, really concerned about, right? And I'm just running you through some of the things that people have been talking about, and this is one, and here's some others, right? So like, there's another thing called intactness, which I told you before is like this sort of how close is the ecosystem to the one that should be there, pristine, right? This comes along with its own problems, of course. Like, what is pristine now, and like, can we ever retrieve what was there before, given that we have climate change and all of that? So there's a discussion to be had about what the baseline here is, but fine. But this sort of ignores invasive species and counts up, and you have what's called mean species abundance. But a Natural History Museum has a biodiversity intactness index. There's a habitat version of it as well, SPI, and so on and so forth. The reason I mention these is these are super, super important in policy at the moment. And they speak really about ecosystem functionality, yeah? How many species are there compared to what was there before? And that's sort of seen as a rough idea of how functional is this ecosystem, which is something we've not talked about yet. We haven't really talked about functionality particularly, although Mario introduced it quite early on with the idea that we actually care about evenness and so on. But this is getting closer to a kind of functional kind of definition of biodiversity. We'll see some more of that later on as well. Then we can think about extinction risk, right? Okay, so like all of the charities more or less are organised around getting money from you to stop species going extinct. Broadly speaking, that is in all of their terms of reference, as it were, their mission statements. So there's a bunch of different ways you can think about extinction risk as well. So here's one, this comes straight from ecology. You can think about extinction risk, this should have an equals sign here, sorry. 1 minus persistence, where persistence is modelled as, like the likelihood that a species remains in a particular place is modelled as a ratio of current area of habitat divided by previous original area of habitat. Okay, so again, it's like a distinct, an intactness type story. How much of its habitat is there in the world? And that's related via this function here with the parameter z to the persistence of this species in the world, right? So as you can imagine, as the proportion goes down, it's more likely to go extinct, the species. So that has various interesting properties as well. You know, the persistence, you've got habitat on the x, you've got persistence on the y, you think about this, but what questions might we have about this function, for instance? Yeah, tell me.
Well, it's not taking into account like how many species are in that area compared to how many there used to be. Like they could be through the whole area, but like have way fewer of them.
You mean it's just using habitat, basically? Is that the story? Yeah, okay. So that's, yeah, and of course it's a species, but you can add in a particular area, you can add up the kind of all the species in a particular area. If you know the current area of habitat in the world and the original area of habitat, you can build up an index over all the species in a particular area. But yeah, it's not really based on these interactions again, is really what you're getting at, I think. Yeah. But it's still very helpful. And usually the way they calibrate, I would have thought Frank would have got you sort of thinking about calibration here, but the Z, where does the Z come from here? That's really quite not very well defined, even in ecology. This is coming straight from ecology, by the way. It's not very well defined. What they used to do is think about islands, small islands of different sizes, and then just count up the species on these islands and say, okay, look, there's a relationship between area of habitat and the number of species that you get, and they would find that it's sort of somewhat this shaped, you know. But if you think about it, those are like steady state situations. It's not really the same as taking a given habitat and then changing a given area and changing the amount of habitat there. So they're kind of slightly different concepts. Anyway, nevertheless, it is used fairly frequently in analysis. In fact, what you can do, you can think about marginal changes as well, but also you can think about cost-effective targeting based on reducing extinction risk. So where would you go in Europe, for instance, if you wanted to reduce extinction risk, this index of extinction risk for the whole of Europe? Well, the red areas are where you would go, and that's a combination of like cost of land being low, but also marginal changes in habitat affecting some pretty rare and close to extinct species as well. So like in the Iberian Peninsula, you've got some like kind of European lynx and relatives there. In Corsica and In Sardinia, you've got kind of whip snakes and salamanders and stuff like that. And then up here, you can see Gotland, there's some kind of vole or something up there, which is really kind of rare. And if you do anything for that, it really reduces the extinction risk according to this formula. So then you've got IUCN Red List. This is like, oh, how endangered stuff are. There's a bunch of criterion that you could use there. I'm just going to skip through that right now. And then you've got some mixed metrics as well. So the mixed metrics, they do exactly the same on the tin, I suppose. You know, you could think about the one, like in the paper with Charlie Palmer that we have, we use this one here, which is like, let's just call it AED, but basically it's the genetic distance measured by branch length, weighted by relative abundance. So it's a bit like the Hill measure, weighted by genetic branch length, so distance to the last ancestor or whatever it is, you know. And then you can change that into a Shannon type of relationship, yeah. So you've got this is the PI times log of PI. These are just proportions. So you can mix these things up and bring in some genetic components to your Hill measure, basically. So we use that. Makes absolutely bugger all difference to the results, in fact, in the UK. And I'm not sort of clear exactly how. I've yet to find a situation where this actually changes any of the results to an analysis. And then you've got Solo's model. This is not that Solo. What time are we on? It's a guy called Andrew Solo. This is a paper with Steve Pulaski and others. Their mixed metric is the following, right? So this is the last one I'm going to go through. You're going to need like a little bit of a deep breath to get your head around it, okay? So yeah, so like if you're thinking of switching off right now, don't do that. Deep breath. So Solo's paper thinks about Weitzman's type measure as well, but also what they call the preservation measure of distance. And they're all based on these distance measures, right? So in this case, this really is the temperature metric that I was talking about before. You know, they have a bunch of data on cranes, and they know these different distances based on the temperature differences I was talking about before. So then DP is the preservation measure. It's just the sum of these distances in a group which is we've got X and Y. So X is you've got an overall set T, you've got X which you preserve, and you've got Y which is not preserved, right? So you've got a limited budget, you've got like 14 cranes, you can only preserve 3 of them in their example, right? So the diversity measure is all about, for the preserved set, it's the sum of distances between species in the preserved set and the ones which are in the non-preserved set, okay? And then you can compare that to the Weitzman type measure, and then you can come up with an expected loss, which is just the difference in expectation between the whole set being conserved and the one you've only got enough money for, okay? So you want to minimize the loss. And the expectation means that you're bringing in probabilities of survival again, right? So this is why it's a mixture. It's got extinction risk in there, but also it's got distance measures as well, okay? So in their example, they have this example here. They imagined 4 species, S1, and these are the distances between them. And they calculate the preservation measure and the Weitzman measure between them, okay? And so you end up, you can't really see this, but they've got set 1 and set X1 and set X2. So this is the one that you're going to preserve. So in the first case, you want to preserve S1 and S3, and in the second one, you preserve S1 and S4, right? And so you calculate the diversity measure to make sure you're preserving the one with the most diversity. So the preservation index for the first one is -2b. Why is that? So you're minimizing the distance between the excluded species and the included one, right? So the included species are S1 and S3, okay? And the minimum distance between the excluded and the included is just the 2 and the 4, so it's 2b, right? Those are the minimum distances between what you've saved and what you've lost, okay? And then for the the other set, so you want to find out whether this is more, if you conserve this set, whether it's more diverse, it's actually minus 3b. So you've got, you say S1 and S4, and so the distance is S1 and S4. So you've got these two, S2 and S3, and the minimum distance is 2b and 1b. Okay, so you've got minus 3b there. So that's less diverse, that one. You want to keep the first one. Okay. But then, cut a long story short, if you go and estimate the Weitzman measure here, which is maximizing the distance between excluded and included species, you end up with A plus B for the first one, A plus 2B for the second one. So this becomes important in this case, the distance between the excluded species and the included one there, maximizing that difference. It gives you a different result. Okay, so the problem is that once you start focusing on like the preservation measure, which tries to get broad coverage of the genetic distances, versus the Weitzman measure, which is trying to maximize those differences between what was saved and what was lost, you end up with different policy prescriptions. Okay, so in the end, the preservation index prioritizes the minimum separation between preserved set and the unpreserved set. Diversity, Weitzman, maximal separation in the preserved set. What's the maximum difference within that preserved set? And this leads to all sorts of problems. So this is their example. They have all of these distances for the cranes. You have the, these are probabilities of survival for the different cranes. They have all the distances here in this matrix. They imagine a policy where you can save 3 by pushing the probability of extinction from whatever it is to 0.1. So that's your policy intervention, and then they see which is the most diverse. There's a little routine that I've got in R, which basically you can download, and this is the kind of ranking that you get from the preservation index, which tries to get minimal difference between the saved, preserved, and the lost set, and the diversity index, which tries to get maximal diversity within the preserved set. There, you can see that the more red it is, the more disagreement there is between Weitzman measure and the preservation measure. So it's ranked in terms of the preservation measure. Preservation measure here prefers 5, 9, and 13 to 5, 9, 14, and 5, 9, and 12. 14 and 12 have higher levels of extinction risk, but the problem is that they also have very close relatives in the preserved set, so they're not that, you don't get that much range from conserving them. You're better off going for 13. So you'll see basically all of this, right? There's a bunch of things that we could go through now, which I'm not going to go through, but to choose between them, thinking about marginal properties and so on. But you can see what's happened here is that we focused in on measuring something physical about biodiversity and thinking about how we want to maximize that or direct conservation money towards this or that in a cost-effective way, right? And mainly that approach has come from the fact that we don't know how to value biodiversity particularly. Because ordinarily, of course, we'd just be going for things that pass a cost-benefit analysis, and we'd be going towards the highly valuable stuff. We haven't said anything about what's valuable to humans here yet, particularly. We've just said, here's some ways of measuring it, and we can use those to cost-effectively meet a biodiversity target. In the next half, we'll talk about some of the values of biodiversity. So let's have a 10-minute break and we'll come back to it.
To be fair, I was gonna
High school. Yeah, in high school. Yeah, high school we did that. It's my favorite song.
One guy.
No, we have like different categories for
I actually
oh yeah, it wasn't like it was which girls like was like no, but it was like one girl who was like who's good at oh yeah, and this kid what was
no, I say so we.
I know, I'm so
With the group, we
kind of
had actually 2 classes, but nobody did.
oh yeah, we'll have like that. I got
What's only girls in there?
any smart thing for us, the Nobel Prize and the next
So now we have
What
I was like, hidden gem. I don't know the hidden gem.
do you mean hidden gem?
no, but you're gonna pick someone out.
No, I don't think about who is the most in the library. I have different associations with people.
So I couldn't say.
Are you
Oh, I know.
telling me
I know
that
one
this
thing
is
like
fake?
I just know it's like this.
I went like very ready to, like research every code. Like,
Wow, I run teams of like
so actually,
people switch that's the word. Like,
But it's also like
Philip.
their warmth,
Yeah.
energy, and personality.
Like,
It's so much.
This is much better than exam.
or it's just
bro,
like
you.
I think it's like
That you do.
it's so
I would not be.
It's going to be. It's going to be 5 minutes. That's a child. Yes,
he's getting all the
which is yeah, like
But you said your
it's not like my
Celebrating and
physical
So is it like hidden gem, like someone who you expect to get bad grades, but suddenly got the good one?
No, it's campus life, not
it's
academic.
more shy or like not so present person.
So
I'm just gonna vote Sophie for all of them.
I would not class one. I would not class one.
Yeah?
it's one day.
Oh, yeah, that's nice.
What's
Oh.
that?
Yes, no, I think I want to
Swiss.
Quick, good.
Is it sweet or?
No.
No, it's a pass.
We're passing. Okay, but I'm having like.
You're going for the hidden gem.
If you have this stuff.
No, he's people's choice.
Oh, they wanna play all the
Because benefit.
Bro, this guy.
I think so.
17.
I think they should have asked for this.
I kan voor de oude opgehen. Ik ben gaan, ik heb niet meer met
No, not that, because when you walk in, I don't feel like
Do you have to
it's not that they have crazy
It's like too long.
So we can go like another.
We usually like go out and we
Just got this. Resting, how much should you
clearly times. That's exactly what my dad had.
My dad was during the
I feel like
and carrot, like we can not toys.
no, but is there
Impaled his on the car. Yeah, that's just gonna win a lot. I'm sure he's Is he dead? Like, don't you go with my party and now he's chilling. Why?
No, so now we have just
Why are you not taking him to the vet? And I was like, okay, yeah. You still have to find the entire quote. Serious, bro? Yeah. She said it was dangling by his head.
it's a group work. It does group work.
I woke up with so many categories. In general. No. No, you're like life is for sure.
For sure.
For sure.
Training now is
Can be because I need my family to come here. So
That's the direct flight.
And you're helping
guys,
them
but then the
once
grades
you
don't matter anymore.
You're helping them once you long.
What?
You're helping them once you're long.
If you go with me, it's choice.
Yeah, I might have a direct flight.
I don't know why you don't have it.
One of them will like bird.
So I'm definitely
How was your trip? It was so good.
going
Wait, when did you get back?
for half an hour. Then I'm having a few
But I found
and then I'm having
yeah, I'm sure no, because you showed me guys. This is like yeah, it's
In the hostel.
no, we're
Crazy
not
day,
like-
really, but crazy day, yeah.
Yeah,
Is it
I know. I think it's Folkestone.
Folkestone.
Yeah.
Folkestone.
And this is not.
It used to be speaking like this.
Because I'm going.
yeah. When?
No. Let's not do that.
Kinda, yeah.
Next week there's probably going to be.
Even the Norway is it?
Yeah, but
Fish fun.
yeah, but I've tried on like an
Spend
extra.
the beyond.
I tried on
So
like
you
an
went
extra
to
bar.
That's where I was.
And then even smaller, so I felt like
Oh, but
So it was kind of,
Then
it was fine. It was like pretty free. What do you guys do? So we like together a little bit of crowd. Outside and went hiking around the area and stuff like that. It was like first time actually snow. I feel like no wait, is it a because like it was like snow is not all bad. I always said that, but it was just really great. I was like, oh my god,
something like this.
actually we do like waitress like in Korea. They have like this. I don't know where to ship
I don't know.
It was like not bad. No, you can try it out. Oh yeah, I actually am down. I mean, I can go to the cinema.
I know.
Oh yeah, that's fine. Maybe we can see we already did,
I would buy it.
yeah, it's fine.
Let's get going.
Actually, my god.
Are you sure?
I mean, you like that activate This thing is then you can also have it like because
Okay. It's really annoying that there's only one screen. I'm really sorry about that. I have just no idea how to fix it. So, yeah. Right. So metrics. Okay, we've had enough of that now. But you know, this is a big part of like research. In fact, there was a review paper which is on the reading list. 600 different metrics for biodiversity in there that they isolated, but they are split down into kind of genetic, ecosystem, species richness, etc. Anyhow, right, so let's start thinking about how, like in theory, we can think about valuing biodiversity. I want to just skip through most of this bit of the paper, but I want to tell you about this paper. It's called The Economics of Biodiversity Losses by a group from Yale, Stefano Giglio and a bunch of other. It's kind of quite interesting perspective on how we might start thinking about how biodiversity contributes to the broader economy, right? So what they do is they think about it, so again, it's going to be like very hand-waving description. That's all you really need just to get your head around it. So they think about economics, an aggregate production function, yeah, that we're all familiar with. Output equals some function of normal inputs, capital labor, etc., which are X, and then E, ecosystem services. So whatever they are, they're sort of water quality, air quality, nutrient cycling, you name it. It's one of those, and maybe even recreation, that sort of thing. Okay? And the way they think about it is as follows, because what their objective here is to think about how to build up from the species. Our knowledge of different species, their function in determining particular ecosystem functions, and how these ecosystem functions contribute to output in the economy, right? So it's an interesting model in that sense that there aren't many of them around. So what they think about is basically that this E part here is dependent upon lots of different ecosystem services, 1 through to G, yeah? And then each one of those ecosystems, again, recreation, water cycling, etc. And then each of these ecosystem services depend on species, right? So let's take this ecosystem G, there's these different species in different abundances N, right? Species 1 through to SG and so on, right? So in order to kind of think about this analytically, you need some sort of way of thinking about the relationship between groups of species and ecosystem services, and then groups of ecosystem services and the overall aggregate kind of ecosystem service, right, that contributes to the macroeconomy. So they make the following assumptions, basically. First of all, again, you don't have to get your head around it, but it's basically, they think about summing up, because you need to aggregate these in some way. So there's summing up over ecosystem services with some elasticity of substitution here, sigma. Yeah, so this is like a classic CES wrapper for these ecosystem services, like you would get in a CES production function anywhere. Right? But their main assumption is that sigma is less than 1, and I don't know whether you've done like the classic Dasgupta and Heel sustainability model, but sigma less than 1 in terms of substitutability, that's a bad sign, right? No sustainability then. And that's the point of this as well. This is them building in the Dasgupta embeddedness, if you lose, it means they're very complementary, these ecosystem services, like shoes, you lose one, then you don't get any benefit from having shoes, particularly, right? So they build in that assumption to this. You lose one ecosystem services, the whole thing goes pear-shaped, as they say in England, probably elsewhere too. Actually, it's different shapes, different fruits they use in different countries, I think, for that phrase. No, you're not jumping in there. Right, okay, fair enough. Let's go with next. And then they think about how you could aggregate up over the different species that feed into the ecosystem services. So like, how do species, relate to and combine and produce these ecosystem services that Mario was concerned about in the very first instance there? Well, here their assumption is, again, CES wrapper to all of this, except now this elasticity is between 1 and infinity. So this is like highly substitutable, yeah? And this is capturing the idea of redundancy of species. There's a bunch of species out there, they kind of do similar kinds of jobs, some of them, yeah? You can lose one and the function that it was performing will probably be taken over by another one. Right? And so there's this functional redundancy of species is what they're building in here. Yeah. So on the one hand, you've got sort of redundancy of species, and on the other hand, you've got high complementarity of ecosystem services. For various reasons, we're going to go. I'm not going to go through all the math here, but basically, the whole point of this is to say what this leads to is a situation where, to begin with, the species are very kind of substitutable. You don't lose much ecosystem service at all. Different species come in, etc., and take over those roles. At some point, you get to a point where you lose one more, like basically all species at some point become keystone species. You lose them, you lose the entire ecosystem service. So this is like the idea of a tipping point built in to coming from species loss, feeds into ecosystem services, and then that feeds into the macroeconomy. Right? So it's trying to build in this big macro level kind of idea of the connection between literally the grassroots of species and our day-to-day macroeconomy. It's a pretty ambitious paper. I would say it's definitely worth, like the motivation for these different assumptions here. You learn a lot about what's been written in this area by reading the introduction to this paper. I think it's pretty good. Okay. That's all I need to say about that. But that's the starting point, really, for thinking like a top level of like the value of biodiversity to economies and to people. Yeah, our dependency on it as well. So one thing, another value which is really kind of and relates to tipping points to some extent, as we'll see, is the value of biodiversity as an insurance mechanism, right? So the idea basically is that you have a more diverse system, and as we saw before with the kind of redundancy idea, the more kind of shocks you can handle, and you can control variability of the things that you're interested in, which could be ecosystem services or profits or whatever it is. You can think about this in terms of like ecosystems, or you can think about it in terms of diverse agricultural practices, where you have different crops being grown within your farm. That can be the diversity that you're thinking about. That has effects on your output and the variance of your output. And that can act as an insurance property. So let's think that through a bit more carefully. So it can be defense from like flooding and so on. So mangroves, like a lot of papers written on this, about how mangroves really offer a very kind of cheap, if you like, defense to storms. Alpine forests, all of these trees here are basically defending this town from avalanches. That's an ecosystem service right there, which is an insurance value. Think about it in terms of agriculture, diversity of agriculture. There's a bunch of different papers here, including one by me and someone who was in your kind of group, as it were, years ago. So he now works at the FAO, looking at how increasing the diversity of the crops that you grow can increase the mean and also decrease the variance of your outputs. Right? So that's an insurance property right there. Okay, so what is the key is, it's easy to say this, and in the natural sciences they say this often, but they don't really nail it down as to what the insurance value is. So that's what we're going to do here, in a very, very simple kind of micro model. What's the definition of insurance, and what's the evidence here that this is true? Okay. What we're going to find is that there are both ecological and economic determinants of whether or not there's a value of insurance from biodiversity. So, let's start here. Insurance, an institution that mitigates the influence of income uncertainty on a person's well-being. All right, so it's all about how we mitigate the variability of people's lives, right? So let's think about it like this way. It can be objective, it can be to do with subjective preferences. Some people are highly risk averse, right? I used to go rock climbing a lot, and when I was young, I took some awful risks. I don't do that anymore. Too many broken bones, and also I've got kids and stuff, and it seemed fair on them, really, and so on. Money, I never take risks with money, ever. Never. I don't see the point. Anyway, so you have like different kind of preferences. So you'll have your own stories about this, right? But it's subjective, and then there's in the face of objective aspects of risk, right? And you've got different types of insurance as well. You can insure yourself financially as well. And we're looking at basically the natural side of things. All right, so this is just a reminder. You all know this kind of thing, but I just want to remind you so it sets up the notation properly. Here's our utility function. It's concave, right? That means we're kind of risk averse already. And we've got two possible outcomes, YL, low, the low outcome, probability P, high outcome, probability 1 minus P. And let's assume we're expected utility maximizers, right? Okay, so our utility from this kind of lottery is basically the probability of the utility we get from the low plus the probability of getting the high one, the utility of the high one. Okay, we get sort of, let's say this is 50%, then we can put the expected value right in the middle there. Yeah, that gives us an expected utility. That gives us also, we can think about the utility of the expected value, and then the difference between those two things is like the difference between the certainty equivalent and the expected value. That gives you a risk premium, right? This is a standard old school micro, basically, isn't it? So the certainty equivalent, of course, is the certain amount that you would be happy to take, which will give you the same level of utility as the lottery, right? And the difference between that and the expected value of the outcome is a risk premium. That's what you'd be willing to pay to avoid the risk. Okay. So in a sense, insurance value is going to be related to this risk premium. How does some kind of activity affect the risk premium that we're willing to pay? And that's how we're going to think about the influence of biodiversity as well. So this is where we go. We're going to think about it in this context. This is from Baumgartner's 2007 paper. It's on the reading list. Very easy read. Stefan Baumgartner is a friend of mine, and he's very, very good at assembling the literature. And he's an ecological economist, and so he has a slightly different perspective of things. All right. So where do we start here? Let's start with some ecological evidence. What is the evidence that biodiversity can actually manage risk? Well, there's not that much around, to be honest with you. It's not, apart from the pictures that I got, but these are like from the 90s, these pictures. And then you have basic species on the x-axis, and then you've got like output biomass on the y-axis. So these are two examples of the mean, effect on the mean. So more diversity, higher mean outcomes for you. But of course, there's a kind of a trade-off. And then with variance, or this is the coefficient of variation, you see more species richness, sort of broadly lower coefficient of variation. So it sort of manages the variance of biomass, okay? So in that context, we can start thinking about the insurance value of biodiversity in some way, right? We can think about, if you want to have any metric you like of biodiversity, whatever, you can think about it as real of species, perhaps, if that helps you fix ideas. Okay, so you've got productivity, you've got stability properties of biodiversity. And here's a model that you can use to think through analytically where these values come from for insurance. Okay, so we've got this kind of stylized relationship that's built in from thinking about definitions of what insurance can be. So we've got the economic value of insurance would be a reduction in the risk premium. How much does increasing biodiversity reduce our risk premium? The way that we should think about this is that we have some ecosystem service that we get. It could be storm prevention, it could be agricultural production or whatever it is, and that's dependent on, it's a random variable dependent upon some different states of the world, right? And these states of the world, we have an index of biodiversity V, they're basically dependent on our level of biodiversity. So we can say the mu is basically dependent on biodiversity, it increases at a decreasing rate, and the variance decreases at a decreasing rate as well. All right, so those are the stylized facts that we got from the empirical work there. Now, given that that's the case, so that's the variance relationship, that's the mean relationship, that's the variance relationship that we have in this model. Given that that's the case, we can start thinking about a kind of a profit kind of outcome. Sorry, that's gone too far. We can think about the benefits from ecosystem services from S, right? And then we have costs of management. So we can push up biodiversity by some amount, but it's going to cost us, and that's just a typical kind of convex cost function there, increasing in V at an increasing rate. Okay. So that means that our net income is whatever we get S from ecosystem services minus the cost. So that's Y is our net income, and that's a random variable dependent upon our level of biodiversity. Okay? So with the mean being the sort of mean minus the cost, and the variance being the variance. Okay. Okay, in that context, we can add a little bit more structure. We say that we've got some, because we want some analytical solutions here, so we add some structure. We say we've got utility that is constant absolute risk aversion, so a Cara utility function, right? So it's exponential. You imagine it would be going down like this, but it's a negative, so it's kind of going like that. Nice convex utility function, okay? And then the expected utility of that is just the integral over that of the over y, which is our random variable. Okay, but this is really neat because this is just like a moment generating function actually. So it's the rho, like rho is our risk aversion parameter. It's the rho moment of the distribution of outcomes here, and that gives you a nice kind of clean expression for your expected utility in terms of mean and variance. Okay, so it's a two parameter utility. We only care about mean and variance in this. You might care about, you know, other order moments of the distribution, but not here. Okay. All right, so that's dependent on our risk aversion here. Okay, from this we can sort of build an analytical measure of the value of insurance. So we can define our risk premium as, remember, it's that kind of the amount that you'd be willing to give up to get a certain amount of income that's equal to the lottery that you face under uncertainty. Okay. But in this context, our risk premium is just that second part of our utility. It's just this rho over 2 times the variance. Okay, so that's our risk premium. And that's a function of V, the level of biodiversity that we have out there. So it can be the number of mangroves that we have out there. It can be the number of species that we're growing, or whatever it is. Yeah? So our definition of the value of insurance is just a derivative of this with respect to V. It's the marginal. How do we change our risk premium as a consequence of having higher or lower biodiversity? Take the derivative of that with respect to V, take a minus because we went to the value of reducing risk, and you end up with this expression here, which is composed of 2 things. Firstly, our risk aversion, rho, but then also of scaled by variance, sigma 1, but then also this ecological part here. So we've got this relationship here reflected in the expression, and this is sort of 2 things that we need to be careful thinking about when we're thinking about the value of biodiversity as insurance. One of them is our economic preferences. The other is ecological sensitivity of the variability to biodiversity. So that's the sigma prime V. Yeah. So we really, in order to establish this, we need to have really good empirical evidence on how much our risk changes, this ecological side, as a consequence of changing the landscape or changing our crop selection or whatever it is. Yeah? Coupled with the fact from a welfare perspective that we need to know our risk aversion. If we're risk neutral and this is 0, we don't care about biodiversity as an insurance mechanism. Okay. So that's kind of really interesting kind of way of thinking through identifying in a kind of crisp way how we can think about biodiversity as being an insurance, having insurance properties for individuals. Okay. Just one last thing about that is that trade-off doesn't always exist, right? So if we were plotting here the production possibilities here, so on the x-axis we've got the variance, and on the y-axis we've got the mean. At some high level of variance, we have a low income. Sorry, we have low incomes, right? Because we have low. Actually, because we have low means. Yeah, we have high variance. High variance. Low V means low mean as well. And at some other extreme where we have extremely high variance, we also have low outcomes as well. And in between, we've got this relationship here. But here, there's no economic problem here. You know, you can increase biodiversity and you get lower lower variance and higher mean, no problem, that's great, we obviously can do that. It's only on this frontier here that we would be thinking about this as actually an economic problem. You've got a trade-off here. You're decreasing variance, increasing biodiversity, decreasing variance, but actually you're losing mean as well, so it becomes an economic problem at this point. Okay? The point being, it's not always the case that increasing biodiversity is an economic issue here. Okay, so that's one way of thinking about it. Now, Stefan and his colleagues have this amazing paper, which is not published yet, and he's refusing to send me the working paper because he's a bit embarrassed by it, but I don't see why he is. It's really fantastic. Check this out. So he tries to calibrate this model to a working situation of almond production in California. Right, so here's your almond farms, there's your almonds, beautiful in the springtime. And what they did was, this is like amazing. So they're thinking about biodiversity in a very concrete sense, like a number of different pollinators, different species of pollinators, yeah? So for like a whole summer, spring and summer period, they had a group of biologists basically counting the number of insects that they found on the almond flowers, right? In different parts of this area in California. Counting them up painstakingly from all over these different trees, different flowers of the trees. So you've got honeybees, you've got wild bees, you've got flies and other pollinators there. And what they found was that the yields, so here you've got these probability distributions of different yields, and here you've got the biodiversity, like here you've just got honeybees, then you've got the next ones, the wild ones as well, and here you've got everything, okay? So what you see there is that more pollinators, yeah, higher means, but also narrower distributions. So it's managing this risk of output in the almond case. So more pollinators, higher yields, narrower, more certain, as it were, production. Yeah. So they calibrated that particular model. And there's a bunch of different results, you can see, you can work through. They really focus in on the fact that the coefficient of variation goes down in the context of this higher levels of biodiversity, okay? So that's very interesting. But it does depend on the parameters of the risk preferences. So they use a CRRA, constant relative risk aversion. That doesn't seem to, in that context, the insurance value is not very high. But if you're mean variance type, if you're a mean variance person, actually that's because of this bit here. If you have CRRA preferences, you've got real downside risk, yeah? And this is a spike of zeros, which for some other reason occurs when you've got in the high biodiversity case. So there you've got this problem with if you have CRRA preferences, you really hate that. So you don't have a high level of insurance value for biodiversity then. But in other cases you would. So it depends on your preferences for risk as to how this all turns out in terms of the economic value of insurance here. Okay. Next thing is, so I want to think about, I don't want to miss out on the last part, right? So that's one aspect of uncertainty that can be managed by biodiversity. It's the insurance value that works on the variance side of things. They have some other work, Stefan and his colleagues, on tipping points and flipping probability. So there's the world of ecosystem services is highly nonlinear. You approach some sort of threshold, you flip over into another sort of world. So ecological systems sometimes have tipping points, is basically the point here. And the resilience that is usually described as a way in which ecosystems can defend from that approaches to that tipping point and keep systems from tipping over into different states. So the figure on the right here is a case of these shallow lakes in Sweden, in Scandinavia, right? So these get kind of, agriculture is big in Scandinavia, and there's a big nutrient load in certain places. And once the nutrients get to a certain point, the state of these lakes just flips over into a completely eutrophied state that you really can't. It's really difficult to turn it back, basically. So here you've got one that's flipped over, and here's one that hasn't very, very close to one another. And this is basically useless from all sorts of perspective. Recreation, there's no fish, there's nothing. It's knackered, right? And this one's fine. So it's gone past that threshold. So we want to manage that somehow and find out what the value of managing those tipping points really is. And so these are kind of basic tipping points idea. You've got sort of the case there is a very stable kind of basin idea. You can imagine the ball rolling around and not really escaping. And then as things get worse and worse and worse, it doesn't become resilient. Yeah, and at some point it shifts over and it's in a bottom. It's in a different basin altogether. So that happens in the context of these shallow lakes. It happens in the context of grazing, right? You overgraze somewhere, the soil just disappears, it never comes back, right? Very difficult for it to come back. Context of overwatering, irrigation, right? You over-irrigate consistently in different places, then you get salination like this. It's really difficult to return this. That's basically irreversible, So all of these are different kind of contexts in which you have sorry, this is all what we did before. So let's think about how we might handle this. So, and this is just two diagrams, so don't get too worried. But basically, the idea is as follows. When you're thinking about the value of resilience, you're working through the probability of this flipping state. So with probability P, you're in the low state, and probability 1 minus P, you're in the high state, a bit like we were before. This probability is a function of R, resilience. And so we're just kind of working through, right, if we change resilience, how much benefit do we get from doing that, right? And there are two things that happen. This is a rather clunky diagram, which I took from their paper. Imagine that you're at 50-50. It's a 50% chance of flipping over into the bad state, 50% chance of being in the good state. And you're able to, with a change in resilience, reduce that to 25%. Two things happen. Firstly, you've got a negative effect on the risk premium like before, so you've got an insurance value. But actually, this is also working through the mean. Yeah? So when you change the probability of being in one state or the other, you change the expected value, and that's an additional value here. So you've got two aspects of this resilience value. Yeah.
Right. When you say like 50%, do you mean like 50% chance of reverting today at this level, or once we reach to this level, we will see tomorrow if it reverts or not, and if it doesn't, then we're good?
We're just thinking of a lottery of possible outcomes in the future, and if it's the low state, it's a low state for good, and if it's the high state, it's a high state for good.
No, like, does the flip mean that like we reach this point, and there's a 50?
Yes.
It moves, and then like, if we do nothing from that point, then we're good. But then if we increase an extra bit, it's 51%.
So we're not working in time really at all here. Yeah. So we're not edging towards like walking along the ice and thinking, oh, well, am I going to go through? No, we're not doing that. We're just saying, look, imagine that we've got these two probabilistic states, a lottery to play with here. We could be here. We could be here. What do I benefit from improving resilience of the ecosystem? So there's two different parts. Yeah.
So we're kind of like decreasing the probability of being in the bad state to 25%, and the high state becomes like 70.
75. Yeah.
And what was the other effect? Because you mentioned the word chew.
So there's the effect. Remember before we had utility is dependent on the mean, and the insurance effect dependent on the variance. Now we've got both of those effects happening. So you've got a mean effect, which is positive. It increases the expected value for you. And then you've got the insurance effect, which decreases changes the risk premium. So you've got these two effects of improving resilience in this context. So that's basically it. I mean, if we calibrate the relationship between probability as an elasticity, of course, it depends again on these ecological relationships, right? The elasticity of substitution, how you change this probability is an ecological and that changes things to some extent. Again, you've got the risk premium as resilience increases can actually go up here, because if you're very close to, you remember what the variance is like if you're in this two-state world. Actually, the variance is highest when those two probabilities are quite even, so at 0.5 basically. So if you move away from very certainly not being in the bad state or the good state, your variance increases, and then it decreases after a time once you get into once you flip over that hill there, and variance starts decreasing again. But the point is that you've got this insurance value which starts negative and ends up positive. It's the marginal effect of this, the marginal of this, but then you've got this expected value effect as well, which is the total economic value, and the difference between the two is the expected value. So there's two different elements of thinking through the value of resilience in the context of this kind of binary tipping point context. All right, last thing, like deep breath, I've got 10, I'm going to use 10 minutes for this. And this is about the value of biodiversity. So what have we done? We've looked at macro values, like the broad brush picture of how species feed into ecosystem services and feed into the macro output. We've thought about insurance values, which is another thing that always comes up because this diversity story has really chimes with the idea of managing portfolios, diverse portfolios and so on. And then there's another aspect of it, it's not the only one of course, is the fact that we think about biodiversity as being a source of new ideas. Right? So you can think about this as biomimicry type ideas, you know, like the nose cone on the train, the bullet train in Japan, that's designed around the kingfisher's beak, for instance. Great idea. It can be to do with medicines and genetic hybridization, right? So we think about evolution as having solved many different problems over billions of years, and we now can use those. It's a source of information for us to solve some of our own life science type problems. Okay? So this idea of bioprospecting, you know, conserving rich biodiversity so that it can help us solve problems in the future is a really powerful one in the economics of biodiversity. All right, I'm going to basically ruin that for you now, in a way. So I'm going to be a little bit problematic. Right, so just to set this up, bioprospecting, cancer treatments, you know, 70% that come from natural compounds. You've got rosy periwinkle, vinblastine, vincristine, this is for leukemia. Utri is for Taxol, right? European, they started with the American U. That became kind of a bit problematic and close to extinction. Turns out the European Utri has similar compounds. Really good solution for breast cancer. Snowdrops, galamantine, that's for dementia. Morphine, you know, lots of different things that we have derived from natural compounds, right? It's pretty impressive. You know, I read in the Dasgupta review that in the 90s, something like 90% of cancer treatments got their inspiration from bacteria in soils. Anyhow, which is fascinating, right? So this brings us back to this kind of Weitzman idea about genetic distinctiveness, I think. I think this is what it does. You know, that is a very interesting measure if you think that you're problem solving for future problems that come on. This genetic diversity is probably like super important for underpinning for this kind of solution, right? Okay. So then comes my friend David Simpson. This is 1996, right? So how old? This is what, 30 years old, this paper now? Yeah, it's 30 years old. God almighty. Anyway, no one's done a better one now, I don't think. I think this might be a rich area for reviewing this. But anyhow, he was thinking about this and thinking, well, is this... So the main argument at the time in the 90s, I was there, and it was basically that this is going to be a really important source of revenue for conservation exercises, right? Bioprospecting, we set up these contracts. Some of them did get set up between Costa Rica and some of the pharmaceutical companies and so on. There are many of them still in place. But the question is, what is this going to be the silver bullet for conservation for biodiversity? So this paper sort of suggests the following, that maybe it won't be. So think about it as the following. So they think about this testing regime. You know, you've gone out there, you've got your sample of compounds from nature, and you're going through and testing them to see whether it's a solution to a particular problem you have, right? And the expected value of testing one of these samples is given, you can think about it as being given like this. It's the probability of success times the revenue that you expect from the solution that you've got minus the cost of testing. Right? So very simple. Right? Test one thing, that's your expected revenue there. Okay. So is that correct? Well, there are some problems here, basically. Some problems of redundancy, right? When we think about individual species being supported by this kind of financial mechanism. First of all, same species are found over a wide geographical area, right? So once you know, it doesn't. In order, let's say you find a solution for a particular species, you don't need to save that entire geographical area, particularly. Right? So that's one thing. Some compounds are found in many different species. So you find them in, you know, the European yew, you find them in the American yew tree. So the solution is not specific to any particular kind of species. Yeah? So again, there's a redundancy there in any given species. Certain populations in excess of the minimum viable populations are kind of, you know, they're not valued at all. You can lose, as we saw from the previous example, there's this redundancy in population. You can lose quite a lot of populations before anything starts disappearing, right? So there's a redundancy there. So there'll be a zero marginal value of losing a particular species when you're at that kind of flat part of the curve there. And then you can get identical drugs which are derived from different species. Okay. And then finally, there's this kind of medical redundancy as well. Once you've discovered the solution from a particular compound, right, you can synthesize that compound and make the same kind of medicines from that, which removes all of the conservation finance from the original solution, right? Okay, so there's all of these different things, and the way that David models this, because it's a formal representation of this, it's all a bit depressing, I realise, but you imagine this testing procedure, right? You've got your sample, and you test the first one, and then if it succeeds, fine, you stop, and then you've got your cache and you've got your solution. If it fails, you go on to the next one, and the next one, and the next one, okay? So what that means is for your sort of value of this process in terms of revenues and expected revenues is the first test gives you this with probability P. And if that fails, with probability 1 minus P, you get the same kind of return. You know, with probability 1 minus P from the next species that you test, the next sample that you test. And then if that fails with 1 minus P squared, you get this revenue here in expectation, and so it goes on with the next and next and next test that you do, right? So you've got this kind of redundancy going on and a truncated value of this profit function here. And it goes on and on and on and on and on until you get to this kind of recursion analytical form here. So the value of your sample of n species is just given by this. Yeah? Okay, but what we're really interested in when we're thinking about individual species is the marginal value of the species. So what's the marginal value of an additional species in the context of this bioprospecting arrangement, given that this is your overall sort of expected revenue from this whole thing? Well, let's have a look. This is your the derivative, like what's the difference between having n species and then having n plus 1 species? It turns out that it's this expression here, right? And that has this kind of shape in probability. So if you increase the probability of a solution being found, which is on the x-axis here, you get kind of quick returns and then really a massive fall off in terms of the marginal value. And the idea is sort of that if you're testing all of these samples and then suddenly you find a solution, right? The rest of your sample is basically worthless from the perspective of this testing approach. And you just stop there and that's it. So the marginal value of a species in this kind of bioprospecting context is extremely small. And they go on to calculate what that might be. Sorry, this is it. With these assumptions here, you get like, let's say you get 450 million for your discovery. It costs about $3,600. You've got 250,000 species. The probability of finding something is like very, very small. These are the kind of values that you get per hectare from bioprospecting contracts. So like Western Ecuador, right? These are the most diverse places on the planet. $20 per hectare in those days, right? And then even some really kind of interesting biodiverse places like California Forested Province, 20 cents per hectare from a bioprospecting perspective. So he kind of really dumped on the whole idea, basically, of bioprospecting being this really interesting source of revenue and so on. What do you think of that? Believe that story? You do believe that story? Yeah. Yeah.
Does this take into account like all of the profits that are made from the medicines created from that?
Yeah. Yeah. That's that 450 million number there. That's your kind of looking ahead expected revenues, present value terms. Yeah.
It's kind of assuming that something's like a